Hi there, welcome along. Another little presentation about little video podcast on line spectra. Of course, the thing that you're looking at is a rainbow, which isn't a line spectra, it's a continuous spectrum. But I just thought we'd start with a jazzy image this time. So just a bit of a recap about what we've seen before. What you got at the top there is a continuous spectrum, so that's all wavelengths and energies present. And then there are four familiar elements underneath, and you can see they've each got their own unique signature of line spectra. So each line there represents a particular wavelength or frequency or energy of photon, and you can see that they've all got their own unique fingerprints, and that's because each element has got its own energy levels. So let's just have a recap about how these lines formed. So we imagine that they were in a tube, a glass tube, with a high voltage, and an electron was accelerated down the tube. It collided with an electron in the atom, causing either an excitation or an ionization. If it gave it enough energy, it would cause an ionization. And we'll talk about that later, but that can be quite useful because that means there are extra electrons available to go down the tube. But if there's less energy involved in the collision, it will cause an excitation, and it will move an electron from the ground state into a higher energy level. That's not a stable arrangement, so the electron has to return to the ground state, which it does by jumping between the allowed energy levels in different patterns. Again, that's something we'll look more at in the future. But each time it jumps down in energy, it gives out the energy it needs to lose to move to the lower energy in the form of a photon. And because there are only certain allowed energy levels, the energy levels are like kind of fixed rungs on a ladder. We use the term discrete, meaning they can't vary over a range. The energies of the photons are fixed, so we get this fixed pattern of line spectra. Just a quick kind of reminder here, the bigger transition here, you can see from n equals 4 to n equals 1 involves a higher energy photon, and therefore is at the blue end of the spectrum. Remember these, the spectrum can extend into the infrared and the ultraviolet for bigger and smaller transitions. The medium-sized transition is a medium energy photon in the middle of the spectrum, and then the smallest transition is the lowest energy photon, and that's at the red end of the spectrum. Looking here, you can see we've got some line spectra from stars, and they look pretty much like a continuous spectrum, and that's because the heat of the star is generating like a light bulb, a continuous spectrum. But there are definitely black lines in there. These are absorption lines, and absorption lines form when we have excitation within an atom. These atoms are in the atmosphere of a star by absorption of a photon. So we're going to head over back to me writing on a bit of paper in a moment, and I'm going to explain what's different about excitation by a photon.
So we're carrying on our look at line spectra, and what we talked about previously was absorption of energy of an electron in the ground state by an electron, and the electron came along, gave some energy and moved on, and that's kind of quite a different situation by the absorption of a photon, which is another way an excitation can cause, because the electron continues to exist and it can carry off any spare energy. So simply what we're saying is along comes a photon, and then it's absorbed by the electron. Its energy, it simply disappears, like in the photoelectric effect, and passes all its energy across. The problem is that well, what we're going to do next, we're going to label these energy levels in electron volts. We didn't do that yesterday, so I'm just going to again invent some kind of typical numbers. And when we do this, you need to be equally happy working in electron volts or working in joules. In some ways, the diagram is much easier to look at and get your head round when it's labelled in electron volts, because these are much more manageable size numbers. But you'll see, it just introduces another step in the maths when we get onto that into a moment. So let's just have a look at how big some of these gaps are. Perhaps wishing I'd gone with slightly easier numbers. That's a 3 electron volt gap, isn't it? That one there is actually, if it was 7.5 to 10.5, that would be another 3 electron volt gap, but it isn't it, because it's 0.3 bigger. So I think that's a 2.7 electron volt gap. Let's just rewrite that, 2.7 electron volts. And 3 plus 2.7, if we want to get the whole gap between n equals 1 and n equals 3, you add those up. 3 plus 2.7 is 5.7 electron volts. And those are the sort of, little calculations you'd need to be doing if you were doing the maths on this, and you'll see that later. Anyway, I wanted to get it out of the way because I didn't want you to kind of, when I discuss the energy of the photon, not be sure how big these gaps are. So let's imagine our photon comes along and it's got, let's do a set of energies. Let's imagine it comes along with 2.7 electron volts of energy. Well, what happens? Well, nothing happens because we haven't got enough energy to get it to the first energy level, have we? So we can't get it to, these are the only allowed energy levels, and they're discrete. There's nowhere for it to go. It can't end up here, so nothing happens. And that's exactly the same as if an electron came along with that amount of energy, nothing would happen. If it comes along with exactly 3 electron volts, that's absolutely fine. Let's maybe put some crosses and ticks on here so you kind of get a feel for the whole thing accumulating, because that allows exactly that transition. It takes it to exactly the right place. There is an energy level there, and that photon's absorbed. And when we were looking at the picture of the spectrum of the star, you could kind of see those very sharp black lines, couldn't you? What about if you've got 3.2 electron volts? Will we get an absorption? Well, we've got enough energy now, but the problem is the photon's got to give all of energy. It can't go off with a spare 0.2. It simply disappears. So no, that's not possible. Had it been an electron, it would have been, because the electron could have carried off the spare 0.2. The next possible is, and I won't kind of insult your intelligence by going on about this forever, is 5.7 electron volts. So 5.7 electron volts would cause an absorption, because that's an exact gap from n equals 1 up to a higher energy level. Right, so we now know that we've got 2 photons that can be absorbed. I'm going to do one and you're going to do the other, in terms of just moving on with some calculations. So I'm going to ask the question, what wavelength, I'll do the slightly harder one, you get the slightly easier one. What wavelength would a photon be if it has energy 3 electron volts? So we've got to do a 2-step process. First of all, I've got to convert 3 electron volts into joules. So remember, 1 electron volt is 1.6 times 10 to the minus 19 joules. And in the end, you've got to know that, although you can get a reminder, because that's the magnitude of the charge and electron off the database, off the data sheet. And then, so that's 3 times 1.6 times 10 to the minus 19, which I believe is 4.8 times 10 to the minus 19 joules. I'm just panicking because I can't see my calculator. There we go, got my calculator. Now we can do E equals hc over lambda. So we'll do the minimum rearranging method this time. 4.8 times 10 to the minus 19 equals 6.63. That's h off the data sheet, times 3 times 10 to the 8 divided by lambda. So we're going to multiply those two numbers together and see what we get. Um, 1.989 times 10 to the minus 25, actually, I just misread that, over lambda, 4.8 times 10 to the minus 19. Now, I know at this stage in the course, your ability to rearrange kind of really varies a lot between students. Actually rearranging these three-part things where the lambda's on the bottom seems to create problems, and that's because it's best done as a two-step process while you're getting your head around it. So what I'm going to do is multiply both sides by lambda, and then that cancels with that, and we've got the lambda up here, and then we're going to move the 4.8 down. So we get lambda equals 1.989 times 10 to the minus 25 over 4.8 times 10 to the minus 19. Just get that calculator so you can see it. That's pretty good. Okay, so fraction button, 1.989, and then on the bottom, so that gives us 4.14 times 10 to the times 10 to the minus 7, and we're just going to tidy that up in a couple of ways. I think that the information I supplied it was in general, I think we did that to 2 significant, actually no, I think we can have 3 significant figures here, because the 2 energy levels up here were labelled to 3 significant figures. But I would rather do this in nanometers times 10 to the minus 9. So 414 times 10 to the minus 9 meters is 414 nanometers, and I now know that's just in the visible part of the spectrum. So when you do the other photon, I think we'll find that you're out in the ultraviolet. So what I'd like you to do is to now find the frequency of that photon. Okay, so stop the video. You have stopped it, haven't you? Good. Got an answer? You're going to tell me what the frequency is? Right, let's quickly go through it then. So we've got E equals HF, but first we've got to convert that into electron volts. You know how to do that because I've just shown you. Let's quickly do that. Uh, 9.12 times 10 to the minus 19 is the energy, and then we're going to do E equals HF. I'm going to rearrange separately now, so we go F is equal to E over H. So we've got 9.12 times 10 to the minus 19 over 6.63 times 10 to the minus 34. Just having a panic now about whether that's right on the data sheet as well. If I put it wrong, so always best to check. Yeah, it is 6.63. So in fact, I'm going to be a bit naughty now. I usually insist on the divide on the fraction button, but because it's already there, the key thing is to use this button down there, and then you don't need to worry about brackets. See, I've shown that my own rule is true. Much better to take your time, put the brackets in. No, not put the brackets in. Brackets they are necessary in some places, but now we've got calculators with fraction buttons, and we don't need it nearly as often. Okay, and we've got 1.3. I'm going to make that 1.4 because the top energy level up here is only labelled to 2 significant figures. We'll go through the rules properly on this. 2 significant figure answer, 1.4 times 10 to the 15 hertz. Great, okay. So you got that. We'll take some more work on that. I hope you got the same answer as me. Thank you.